Alrighty, so today we are doing AP Test Prep Level 2D. Okay, not quite 3D, 2D. We are going to be looking again at our Lewis structures and how resonance slash formal charge is found. And then if we have some extra time, we can start going into hybridization. Okay. Now, let's see here. We'll start with, I think the best way to understand formal charge is to go through polyatomic ions. Okay. So one of the polyatomic ions is NH4. Okay, NH4, and it has a +1 charge. Okay, now we want to find the formal charge on each one of these elements in the compound. Okay, so first we have to make our Lewis structure. So we have nitrogen, which has 5 valence electrons. We have 4 hydrogens, which each have 1, so that's 4 valence electrons. Now we have a +1 charge, and so we have to get rid of one of those electrons, and so it would be a total of -1 electron, and then that would be a total of 8 electrons. Okay, now when we draw, we have our central atom, and we make a bond to each one of the other atoms. Okay, now we count the number of bonded electrons. That's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we have used all of our electrons in showing bonding. I hate that this doesn't erase. And so we don't need to add any more electrons. Why won't you erase? Okay, we'll leave it. Now, formal charge is a specific calculation. Okay, this calculation tells you the charge on the entire atom or on the entire molecule based off of the types of bonding and the electrons present. The equation goes: formal charge is equal to the number of valence electrons minus the number of non-bonding or lone pair electrons, and then also minus the bonded, we'll actually move this over, bonded electrons divided by 2. Okay, so if we look at the hydrogens here, the hydrogens have 1 valence electron, they have 0 lone pairs, and they have 2 bonded electrons, and divided by 2, that is 1, so 1 total at the end, and so we have a total here of 0. So each one of these hydrogens has a formal charge of 0. It is neutral. Now, if we look at the nitrogen has 5 valence electrons, it has 0 lone pairs, and it has 8 bonded electrons divided by 2, that is 4. And so 5 minus 4 is a +1. Okay, and so the formal charge on nitrogen is a +1. If we add all the formal charges of each one of these atoms together, we get a total charge for the molecule, which is +1. Okay, and that is how we find polyatomic ions. Okay, let's try one more. CO3. Okay, carbon has 4 valence electrons. Oxygen has 6, and there's 3 of them, so that is 18 valence electrons. Now, it is a -2 charge for carbonate, and so we have to add 2 more, so that is a total of 24 electrons. Okay, Now, when we draw this, we have CO, double bond O, O, 1, 2. We have to count the bonded electrons first. So we have 8 bonded electrons, and that means we have 16 electrons left. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. Now, we want to look at the formal charges of each of these. Carbon first. Carbon has 4 valence electrons, has 0 lone pairs, and it has 8 bonded electrons divided by 2, that is 4. And so its formal charge is 0. Let's go with this oxygen, the double bonded oxygen. Okay, this double bonded oxygen, it has 6 valence electrons, it has 4 lone pair electrons, and it has 4 bonded electrons divided by 2, that is 2. And so 6 minus 4 minus 2 is 0 as well. So there's no formal charge on that oxygen. Now, these two oxygens are the same, so we can just do one formal charge calculation. They each have 6 valence electrons. They have 6 lone pairs, and then they have 1 in the bonded electron realm, and so that means it has a -1. So each one of these has a -1 charge on it. When we take the total of all the atoms, we get -2 charge. Okay, and that is the polyatomic ion for carbonate. Now, we can transition into resonance from this carbonate. Okay, carbonate has this Lewis structure. And in real life, there's no way that we can recognize between the oxygen number 1, number 2, or number 3. Okay, they are all fairly similar. One of them has a double bond, yes, but in resonance, what that means is that this double bond, I'll circle it in red, this double bond can move around the molecule. Okay, electrons move continuously, and so that double bond could be on this oxygen or this oxygen. Okay, as long as the electrons move around in a synchronized pattern. Okay, so I'll do this in red. So say this double bond moves over here. That means, say this double bond moves up here. Well, I shouldn't start there either. Say these lone pairs move down into a double bond. That would be too many bonds on carbon, and so this bonded pair of electrons has to move up onto that oxygen, and that would give us that molecule with the double bond on this oxygen. Okay, and the same thing can happen again. What if this lone pair goes down to bond, and then now this bonded pair has to go up here? Okay, that would give us that molecule. So in all reality, and what reality happens is that these are all resonance structures of each other. Okay, they are still the same molecule. Essentially, you could just rotate that molecule like 120 degrees or something, and it would be the same molecule. Okay, however, in reality, since that double bond can be on any one of those oxygens, the molecule looks more like this. Okay, and then there is a partial double bond on each one of those. Okay, those electrons do not stay in one spot. If they have the ability to move, they will. And so, in real life, the molecule looks more like this. So there's not a full double bond on any one of those. If we take a snapshot in time, maybe it does, but we can't do that. And so we get something like this, where you have partial double bonds on each one of those oxygens. Okay, so those resonance structures devolve into something that looks like that. Okay, now these double bonds move, and they can move in terms of from one highly electronegative atom to another. Okay, they have to have an electronegative atom to go to, and they also have to have lone pairs to replace the double bond that leaves. Okay, so something like this will not have resonance. Okay, this double bond, if it goes up here, there's no lone pairs on hydrogen to replace the bond that's being lost. Okay, actually, I put one too many hydrogens in there. So there's no lone pairs on this hydrogen to replace the bond that's lost here on carbon. And so this molecule cannot have resonance. Okay, something like this. Okay, this also would not have resonance. Okay, even if this double bond moves up, you cannot form a double bond with chlorine. Okay, chlorine does not make double bonds. It only wants one extra electron, and so it cannot form double bonds because you're overruling the capacity for that atom to form bonds. You'd be putting a formal charge of +1 if you moved these down into a double bond, and formal charges are not easy to make. Okay, so formal or resonance only happens when there's something to take, some lone pair that can take the place of the moving electrons. Okay, something like benzene. Okay, there's a carbon at each one of these vertices, and there's a double bond here, here, and here. Okay, these double bonds can move around because these double bonds can switch places as well. So if this double bond moves here, then that one moves there, and that one moves there. Okay, and so the resonance structure, and you can see benzene drawn like this normally, looks like that. Okay, with a better drawn hexagon. Okay, so that circle means that those double bonds are equally distributed across every single bond present. Okay, resonance is a very difficult topic to get into and understand, because you have to have some experience in like some organic chemistry kind of to really recognize where an electron can go and where it can't go. So resonance is a very difficult topic, but I suggest getting practice with topics like that, or examples like this. Okay. Now, lastly, we have hybridization. Okay, hybridization is also another difficult topic. Like I said, these videos are not to teach you the topic from scratch. They're bringing the information that you took notes on before to the forefront. So, hybridization. Okay, we've already talked about electron configurations. And in electron configurations, we had the s, p, d, and f orbitals. Okay, s orbital has one suborbital. The p orbital has 3 suborbitals. The d orbital has 5 suborbitals, and the f has 7 suborbitals. Okay, each one of those suborbitals can hold 2 electrons. So the total electrons held in s is 2, total in p is 6, the total in d is 10, and the total in f is 14. Okay, now when you make bonds in a molecule, take for instance CH4, okay, we form the molecule here. There is a bond between the valence electrons in carbon and the valence electrons in hydrogen. Okay, now the valence electrons are in the for carbon, they are is it 2s? Let me make sure. All right, the valence electrons for carbon are in the 2s, so it's 2s2 and 2p2. Okay, it has a total of 4 valence electrons, and if we were to draw this, we would get a 1 electron there and 1 electron there, and then the p electrons would be 1, 2, 3, 1, 2. Okay, so total of 4 valence electrons. When you look at that, you see, well, ironically, carbon only looks like it can form 2 bonds, right? Because there's like 2 empty spaces there. However, these are the valence electrons, so they're very movable. And so when carbon gets ready to make a bond, okay, it will move 1 electron to that area, and so the drawing looks more like this. Cool. Now it has 4 areas to make a bond with. Now these orbitals, okay, this would be called an excited state. Okay, an electron will move up an orbital, and this becomes an excited state. So we have an s and 3 p's. Okay, and then when it gets ready to make a bond with each one of these hydrogens, okay, it is using these changed orbitals to form an sp3 orbitals. Okay, it combines the 1s orbital and 3 p orbitals to form to form 4 sp3 orbitals. Okay, these sp3 orbitals are then allowed to bond with the s orbitals in hydrogen. Okay, and so the p orbitals that originally looked like this now look more like this. Okay, this is now an sp3, and there are 4 of them, and so you get 1, 2, 3, and then 4. And it's going to bond with a hydrogen at each one of these spots. Okay, this is a very confusing sentiment, but the easy thing to look at then is that every single tetrahedral, or something with 4 things off of the central atom, is going to form sp3. Okay. anything that is trigonal planar will form sp2. And then anything that is linear will form sp. Okay? Linear in the sense of there are 4 things off the central atom, 3 things off the central atom, and then 2 things off the central atom. Okay? Now this is a callback to last video. This is where the shape naming comes in. Okay? Anything that has 4 things, including lone pairs, off the central atom will form sp3 orbitals. Trigonal planar will form sp2 orbitals. So if we look at something like Bf3, we have boron, which has 3 valence electrons. Okay, which means it has the 2s2 and the 2p1. And so it's going to form that electron getting excited. So it's going to have 1 s and then only using 2 of the p orbitals. Okay? It's only using 2 of the p orbitals. And then the same thing for a linear molecule. Okay? So that is a lot of information that we just covered. Okay? We covered formal charge, resonance, and hybridization. Okay? Take your time, watch the video as many times as you need, go back, look at your notes, look at your textbook, and connect the two. Okay? Stay healthy, stay safe, and good luck studying.